All right, if a t-test is the most common way to compare two groups of numerical scores, then we need something to carry out the same function, but when we're dealing with more than two groups of scores. And that's where ANOVA comes in. So ANOVA is short for analysis of variance, and it's an inferential statistical test used for comparing three or more groups on a numerical variable. Specifically, we're talking here about what we call a one-way ANOVA, meaning an ANOVA with a single categorical variable. That's the groups, right? That one factor, that's the groups. And then you're measuring as a dependent variable, a single outcome, a single numerical variable is your DV. Now, you can get fancier with fancier versions of an ANOVA where maybe you have multiple categorical variables. That'd be multiple factors, we'd say. So we call that a factorial ANOVA. Or you can even have a type of ANOVA with multiple dependent variables, things like that. But we'll stick to the simple case here, which is often just called ANOVA for shorthand, but it's a one-way ANOVA technically. One factor, one independent variable. So we're going to be comparing three or more groups on a number variable. Let's start with an example. Imagine the National Transportation Safety Board wants us to examine the safety of compact cars, mid-size cars, and full-size cars. Maybe we want to test and see if one of those categories is more or less safe than the other categories. So they sample, let's say, 20 cars of each size and perform a crash test on them. We want to know, does car size make a difference for safety? Well, we've got a grouping variable here. That's car size, so it's a factor, and there's three levels of that factor. Then we'll separately have a dependent variable, which is the numerical thing. The DV is our safety score of 0 to 30. That's the outcome. Now, instead of trying some fancy new test like an ANOVA that we'll talk about in a moment, I could actually try solving this problem by using a tool I already have at my disposal. Maybe what I would do is just use a t-test for every combination of those groups. So in that case, I would do an independent samples t-test comparing compact cars to mid-size cars, maybe using the standard alpha cutoff of 0.05, right? A 5% chance of false positive, of a type 1 error. Then I would separately do another independent samples t-test, this time comparing compact cars to full-size cars. Again, with an alpha level of 0.05, so another 5% chance of a false positive. And then finally I would do a t-test comparing mid-size cars to full-size cars, again with a 5% chance of a false positive on that one, in addition to the other two. Now, if all those null hypotheses are true, let's say there's no difference in safety for car sizes, then the probability of me avoiding a false positive would be, well, let's see, if there are 5% chance of false positive, then it'd be 95% times 95% times 95%, which is only an 86% chance of totally avoiding a false positive. But that means there's a solid 14% chance of making at least one type 1 error, at least one false positive. That's a problem, because that's happening even though we're using an alpha level of 5% chance of false positive in each individual test. But doing additional tests really adds up our risk there, doesn't it? And indeed, if I was comparing, let's say, 5 types of cars, that would actually be 10 different t-tests I'd have to be doing if this was my strategy. Type 1 versus type 2, type 1 versus type 3, type 1 versus type 4, and so on. With an alpha level of 0.05 in each of those 10 tests, that means even if there's no real difference, even if the null hypothesis is true for all those tests, you would still have a high chance of getting a type 1 error, of ending up with a false positive. The odds of avoiding that would be 95% to the 10th power, since you're doing 10 tests, but that is only 60%, meaning you have a 40% chance of at least one false positive showing up. So doing a whole bunch of individual t-tests to make each set of possible comparisons, it just isn't a great strategy. And that's why we developed a better option. We can use a stats test that can compare more than 2 levels at the same time. That's what ANOVA is good for. And again, that just stands for analysis of variance. So here, we're going to set up a single statistical test where the null hypothesis will be that every group, every level of my factor has the same mean. So mu1 equals mu2 equals mu3 and so on for, however many groups I have. It's just easier sometimes to write it out as saying all means are equal. All groups are equal. That would be the null hypothesis. The mean of all levels is the same. There's no difference among the conditions. That's the null hypothesis. No difference, no effect. But that means the alternative hypothesis has to be the opposite, the complement of that. It says there is at least one difference. At least one of the means, at least one of the groups will differ from the others. So that's how we set up the hypotheses for an ANOVA. And as far as how we test that null hypothesis to see if we reject it, we're going to do things similar to a t-test or any other null hypothesis significance testing. We're going to start by writing down our hypotheses, which they'll always look the same. They'll always look just like this for an ANOVA. And we'll choose an alpha level, which usually is 0.05, so 5%, right? Then on a probability distribution, what you do is you just cut that 5% alpha value into the like 5% in the farmost tail. It's actually easy with an ANOVA because this is always one-tailed. So you're always putting all 5% of that alpha value out in the tail, with the other 95% of the graph being in tan here. Then you can look up in a table what critical F value would be considered statistically significant, meaning what F value would represent the least likely 5% of F values one might get from samples of the size you're taking. This is like a target F value, and you're going to see if your sample's F value is bigger than that, and thus out in the critical region, or what we might call the rejection region, where you would reject the null hypothesis and conclude that the groups aren't all equal. So then the next step, like once you've looked up that F cutoff value, the next step is to calculate your sample's F value. So you can see if it falls beyond that cutoff or not. If your F value is bigger, if it's out here, then you're in the rejection region, right? So if yours falls beyond the cutoff, you would reject the null hypothesis. If it doesn't, we say you would fail to reject the null hypothesis. In other words, you can't really conclude much. Now, what do I mean when I say calculate an F value for your sample? This is where that name analysis of variance comes in. We're going to calculate something about how much variation there is between the different groups. And we're going to compare that to just how much normal variation there is within each group. So let me see if I can explain this. Let's start by thinking back to what a t-test calculates, where we get a t-value along the way to find out if the test is statistically significant. If you look up at the top here, these are the equations we use to calculate a t-value for an independent samples t-test, a dependent samples t-test, and even a one-sample t-test. In all cases, the t-value is basically how much of a difference you found and dividing that by SEM, the standard error of the mean, which is basically just a fancy standard deviation that takes sample size into account. So conceptually, the t in a t-test, the t is just a way of counting how many SEMs the difference was. How many steps of variation apart things were in your sample. It takes the difference, the variation in your sample, and just counts it in standardized steps based on the normal amount of variation in this type of thing. So look up at the top again. With the independent t-test, you look at how much variation there was between the mean of group 1 and the mean of group 2. That's the variation between that I highlighted. And you're dividing it by the standardized amount of variation, just how much there is in this variable in the first place, based on the variation within a given group itself. And it's the same idea for the other two ways of calculating t here. The m with a little d is the mean of difference scores. So that difference score is referring to the variation between your conditions, right? And you divide that by a measure of how much variation there is in general in these things, which we've called SEM. Okay, so that's the idea of what we calculated in a t-test to see if that t-value is extreme enough that we would reject the null hypothesis. So if we're doing that in a t-test, then what are we doing in an ANOVA test? Well, in ANOVA, what we calculate, it's called an F value, but it's the same idea, just kind of lumped across 3 or more groups. So the F value is going to look at how much variation there is between all your groups, like how different are the samples you took for each group, Was the safety score maybe super high for mid-size cars, but a bit lower for full-size and lowest for compact cars? How different were those groups' averages? That's the top part of this equation, the difference between groups. Then we just divide that by the variation within groups, which means like how much this variable tends to vary and spread as a general thing on its own anyway. So like even within compact cars, there'll be some variation in safety, right? And ditto, within mid-size cars, there'll be some variation in safety. So we can figure out an estimate of how much things are expected to vary, just how much safety in general varies. And we're asking how many steps of that our variation between the groups is. That's why we divide by variation within groups. It's just how big is the difference between our groups relative to the kind of differences and variation we see anyway. So that'll tell us if it's a big enough difference between the groups to be significant. Now, how would we calculate this variation between groups? You won't actually need to carry it out and calculate anything, especially if you have a statistics program. But I want to walk through at least the idea of the calculation, just so you have a feel conceptually for how it works. So we're going to be looking at something like variance, between the groups divided by variance within the groups, right? So when we're thinking about how we get that F value, it'll help just to review real quick, remember the idea of variance, which is just standard deviation, a familiar idea. Standard deviation, but variance is standard deviation squared. And how does variance get calculated? Like maybe you've run into this in a previous statistics course. Well, to calculate variance, which is standard deviation squared, to calculate that, we see how much each score differs from the mean, the sample mean, the average score, right? So that's the x minus m here in parentheses. It's how far a given score is from the sample mean, which you can think of as its deviation from the mean. Then we're going to square each of those. We square each of those deviations, so that's the square in the parentheses bit here, and then we take the average of all that, the average by adding it up. This is the summation sign. So adding it up and dividing by the number, or at least the number minus 1 in this case. So variance is the sum of squared deviations. So you add up the sum of squared deviations divided by n minus 1. And we actually call this n minus 1. We call it degrees of freedom, df for degrees of freedom. But it's basically just sample size n with a little adjustment, okay? The point is, notice when we're calculating variance of a sample, we're doing this sum of squared deviations, the SS, divided by degrees of freedom. SS over df is a way of giving average squared deviation, right? You add things up and divide by the number, that's an average, that's the mean of something, right? And we're doing that on the squared deviation. So in this case, it's a way of measuring how much spread there is, how much difference there is in something. You'll actually see this pattern of SS over df in multiple places in statistics because it's just an average. You add something up and divide by how many scores there are. That's an average, that's a mean, sum up, divide by how many. So conceptually, variance is average squared deviation from the sample mean, average spread. Or you could say the mean of the squared deviations. Well, we're going to do the same thing when we calculate an F for the ANOVA test. Remember, ANOVA will involve calculating an F value, which is the variation, or we could call it now the variance. The variance between our groups divided by the variance within our groups. And what is variance? It's the average squared deviation. Sum up the squared deviations and divide by the sample size. Sum of squares divided by df. That's the average squared deviation. What we might call the mean squared deviation, since it's adding up and dividing by that many. And the mean squared deviation is kind of a nice term for this, so you're going to see it used in statistics programs a lot. Indeed, we can calculate that variance, that mean squared deviation, between our groups. That's what we want up top here. The variance between groups, the mean squared deviation between our groups. And then we want to divide that by the mean squared deviation within our groups. In other words, the variance within our groups. That is what we would need to get our F value, right? Those two pieces. Like if we calculated it out and we got a mean squared deviation of 92.8 between groups, right? So that's the variance between groups. Then divide that by 6.27 if that's the variance within groups, the mean squared deviation. That's variance within groups. Divide 92.8 by 6.2 and you get about 14.8. That is our F value. At which point we can look that up, see what p-value that corresponds to see if it's statistically significant. But you might be wondering, where did these red and blue bits come from? How did we calculate the mean squared deviations, the average squared deviations? Remember, those are a measure of variance. So it's summing up squared deviations and dividing by the number of things. Its variance is SS over DF. So sum of squared deviations divided by degrees of freedom. Variance is always that. It's always sum of squares over degrees of freedom, since that's average deviation. That's what we'll see here, SS over DF as a pattern. And indeed, that is how we get to the red and blue values. We calculate a sum of squared deviations between our groups and divide that by the DF, the degrees of freedom. So for example, 185.7 divided by 2 gives you 92.8. So the red box, the mean squares between our groups, the variance between our groups, it's just the top of the F value we wanted, the variance between groups. It's the mean or the average squared deviation between the groups. And we do the same for the within groups variance. We do SS over DF to get the average squared deviation, the mean squared deviation. That's what they call mean squares here, right? But you can think of this as just variance. Mean square, by definition, is variance. So this is variance between groups and variance within groups, which means we have what we need for the F calculation. So this thing here, this table, this is called an ANOVA table. It just shows you conceptually where an F value comes from and how it really does just measure variance between groups divided by variance within groups. 92 divided by 6, you get 14. Right? It's the same as saying average squared deviation between groups over average squared deviation within groups. Now, of course, we would still need to calculate where those SS between and SS within values come from, but that's beyond the scope of this overview since I don't want us actually hand calculating an ANOVA at this point. You can get that with a statistics program, of course. I just want us to understand the concept of what an F value is, and you can see how it's the exact same concept as a T value. You're counting how far apart the groups or conditions are in your sample, and then reporting it in terms of how many normal steps of variation that is. And again, the point of all this is that we calculate an F value, a measure of how much extremely the groups varied, how extreme their differences were, so that we can determine if that's likely to happen when the null hypothesis is true. If it's like very unlikely to get so much variation between my groups, if it's very unlikely to get an F value this large when the null hypothesis is true, then we'll reject the null. And again, you can look up in a table what F value counts as large enough, and you can, from that, you can actually get a specific p-value. So you know the p-value of your sample data. With that, you can always just see if your p-value is below 0.05 or whatever alpha level cutoff you choose. Because a p-value is just the probability you will get samples with this much variance between them, this much variance between your groups, if the null hypothesis was true. That's what a p-value is. If the null is true, how often would you find this big of a difference between your groups? And if it's super unlikely when the null is true, then we would reject the null and conclude there's some real population level difference in there between your groups. So just thinking about what it would mean to reject the null hypothesis in an ANOVA, how do we interpret things when that happens? So I've kept our hypotheses written up top just to make it nice and clear. But imagine we're rejecting the null. So we got an F value that was really far out on that graph in the rejection region. Another way of saying that is we got a p-value that was low enough, it was below 0.05. So we reject the null hypothesis. That means mu1 and mu2 and mu3, all the means of all your groups are not equal. So at least one of the groups or conditions is different from at least one of the other groups or conditions. In other words, you can conclude that at least one mean differs, at least one group differs, but we don't know which group or groups differ from which other group or groups. Which means we're lacking some of the most interesting and important information we might want from our data when we do an ANOVA. So in that case, if you reject the null hypothesis doing an ANOVA, you actually will need to also do a follow-up, which we call post hoc tests, meaning tests done after the fact. These are follow-up statistics to compare each pair of levels to see what differs from what specifically. Now, you don't need to do these if the ANOVA wasn't statistically significant. So you don't do these if you fail to reject the null hypothesis. At that point, you don't have any overall evidence that a difference exists anywhere in the groups. So you don't bother risking more false positives by doing all these follow-up tests. But let's imagine our ANOVA was statistically significant. Let's say it had a big-ass F value, which we realized was out in the critical region, meaning our p-value was below 0.05. So let's say we rejected the null. Now what we do to do the post hoc tests, probably we'll have a statistics program, like SPSS or R, do them for us. Now conceptually, it's going to be kind of similar to doing a t-test comparing each pair, but in reality we use a fancier method like Tukey's post hoc method to compare each pair in a way that's less likely to generate false positives. I'll show you an example in the next slide, but try not to get too overwhelmed by all the statistics program output that I show. I will walk you through it. So imagine, this is just for an example, we're testing fertilizers. Maybe we tested 5 different types of fertilizer on different patches of land to see which fertilizers worked better or worse than the others. So our independent variable, the factor, was fertilizer, and it had 5 levels. Then our dependent variable was something like how much yield we got, how much growth or output we got from that plot of land. So let's say we ran an ANOVA already. We ran an ANOVA comparing our 5 groups, and it was statistically significant. So we rejected the null hypothesis. We have already concluded there is a difference somewhere between these 5 fertilizers, but we don't know what it is yet. We need post hoc tests now. We want to know which fertilizers had more yield than which other ones. Now you can see we've named the fertilizers 1, 2, 3, 4, and 5. So in the chart here, if we just look at the top chunk, the top set of lines here, we're doing a post hoc test comparing fertilizer 1 to, on the top line here, comparing fertilizer 1 to fertilizer 2. That's just the topmost row. And it tells us the mean difference, so the average difference, like plots with fertilizer 1 had about 10.6 more yield on average than plots that used fertilizer 2. Now the question is that difference, is it statistically significant? Is that significantly more when you use fertilizer 1? And for that, we have to search the output for a p-value somewhere here, which in this case, this is from SPSS, the stats program called SPSS. It labels the p-value sig, for significance, short for significance. So these little numbers under sig, those are p-values. Each row here is a specific comparison, right? So the p-value is, the test for 1 versus 2. The next will be 1 versus 3 p-value, and so on. So in this case, if the p-value is 0.000, I'm going to assume there's a trailing 1 somewhere out there. It can never be actually 0. But it's less than 0.001, right? So we did find a statistically significant difference between fertilizers 1 and 2. Then we can just go to the next row down. The next row down, we're comparing fertilizer 1 now to fertilizer 3. And we see, on average, its yield was 5 higher when you're using fertilizer 1. But is that difference statistically significant? So we go over, and the p-value of that comparison test is 0.012, which is below our usual p-value cutoff of 0.05. So yes, this one is also statistically significant. Fertilizer 1 gives significantly more yield than fertilizers 2 or 3. The next line then shows 1 is not significantly different from 4 because the p-value is not below 0.05, right? And then the last line up there compares fertilizers 1 and 5. And the p-value here is below 0.05, the usual cutoff, so yes, it is significant. So now we know fertilizer 1 gives significantly more yield than 2, 3, or 5. But we still want to check, like, how does 2 compare to the others? How does 3 compare to the rest? And so on. So we would just continue looking down the SPSS output here until we've checked each comparison and see if the p-value in that sig column, the p-value column, was statistically significant. So that's actually the rest of the comparisons that I've drawn arrows to here. That covers all the possible comparisons. So this is what we're referring to with post hoc tests after an ANOVA. Like, we first just did an overall ANOVA to check if overall is there a difference between the groups in any way. And only if that's statistically significant and we reject the null, only if the ANOVA was significant, do we then go and run all these post hoc comparisons. But thankfully, in any modern statistics program, you're literally just telling it to run an ANOVA, and you mark a checkbox to say, yes, if it's significant, please report post hoc tests using something like Tukey's method, which is a common one. And it'll crank out a chart like this for you to look at without having to hand calculate anything. And once you've seen something like this a few times, it's way less overwhelming than it might look at first. But the big takeaway is, if an ANOVA is significant, you only know there's a difference somewhere among the groups, but you still need post hoc tests to find out where that difference is. Whew, okay, that is enough info for an overview of what a basic one-way ANOVA is, and where the calculations for it come from kind of conceptually, even if you never end up doing those calculations by hand. Just like a t-test, we are measuring the variation between the groups in our sample, how far apart they are, the difference between our groups, but we're going to report that in terms of the normal variation we see within the groups. So if it's a big difference between the groups, if the numerator is much bigger than the denominator, then we're seeing an unusually large difference between the groups in our sample. So if that's unusually large enough compared to what we would expect if the null was true, then we reject the null. It's the same logic for a t-test as for the ANOVA, and honestly that's because the t-test is actually just a special case of ANOVA. Technically, ANOVA works just fine even with 2 groups, and the numbers all crunch out identical to a t-test because it's literally the same process. The t-test is just a special case with only 2 groups or conditions rather than 3 or more. Now in other videos, I'll talk about tests we might use in different situations, like when you've got a couple of categorical variables, no numeric variable, and maybe we want to know if those 2 categorical variables are related. That would be like a chi-squared test. Stuff like that will be in another video.